So we're going to look at vector, parametric, and symmetric equations in 3 space. So a little different from what we were doing before. Before we worked with just 2 space. And we'll scroll down here to a couple examples. In 3 space, our coordinate, instead of just writing an x and a y value, we also have a z value. There's a third dimension involved. And we can write it very similar to how we had before. In fact, this is the exact same as in 2 space. The only difference is our naught in this case has 3 coordinates. And our directional vector m also has 3 coordinates. Okay? And we know it can also look like this, where our x, y, and our z are equal to x naught, y naught, z naught. So a coordinate on that vector plus our parameter multiplied by our directional vector. That's for a vector equation. Our parametric form, all we're doing is taking these equivalents and setting it equal to our x. So x is equal to x naught plus t times a, which is our parametric form of x. Same with parametric form of y. We just set up the second values in each. And for z, we set up the third values in all 3 of those. And that would give us our parametric form. And finally, our symmetric form is a little different. We're getting 3 equivalents, and the 3 equivalents are equal to the parameter, t. So t is equal to, and we set each of our parametric forms. It's easiest to go from parametric to symmetric form. We set each of these values equal to the t in the parametric form. Okay? And in these cases, our a, b, and c value can't be 0, otherwise it doesn't exist. Okay? So need to know, blah, blah, blah. Okay, so let's actually put some numbers to this so this kind of makes sense. The first thing we need to do is figure out how to find a directional vector in 3 space. And it's just something we already know how to do. To find the directional vector between vector AB here, we take the coordinates, and we would take x2 subtract x1 for the x value of directional vector. We would take y2 subtract y1 for the y value of the directional vector, and z2 subtract z1. Okay, so this being x1, y1, z1, x2, y2, and z2. We're going to take all these values and we'll get a directional vector when we put it into this process. So we'll call this vector r in this case. Okay. We know that it is equal to, actually no, we'll call it OP for a positional or directional vector. Vector OP. x2 being -3, x1 being 6, y2 being -5, 1 being 4, and x2 being 2, and z2 being 2, z1 being the value of 1. We're going to end up with -9, -11, and 1. Okay, so our positional vector is at this point from the origin. Okay, so now that we have that, we can go very easily into our vector form of a line. Okay, so vector form. Remember, the vector form is usually written as r is equal. Oh, thank you. Right. -5 minus 4 is -5. R naught being a point along that vector, which in this case will be this point here, plus t again can be our parameter, and they call it vector m. Sorry, I wrote that wrong. This is our vector m, because this is our positional vector. Our point on the vector can be either A or B. Okay? And in this case, we'll take vector B to be our point. So this would be considered our R naught. Okay? I can take A or B. Sorry, I said that wrong. I misspoke earlier. So vector R is equal to, like we said, we're going to take coordinate B, which is -3, -5, and 2. -3, -5, and 2. Plus the parameter times our directional vector, which is, in this case, what we found before, -9, -9, and 1. So this is our vector form of a line in 3 space. Okay, that's the first step. The second thing we want to work on is how to go from our vector form to our parametric form, which is very similar to 2 space. The best way to probably set it up is to replace our vector r with the coordinates x, y, and z, and then rewrite the same vector form, and that way we can easily match up coordinates and parameters. So, for parametric form, we're going to have 3 equations. One of the equations needs to be set equal to x, one to y, and one to z. For our x equation, we take x is equal to the first point multiplied by the x value of the directional vector times our parameter. So x is equal to -3 minus 9t. For y, we do the same thing. We just set up all the y values with each other. Y is equal to -5 minus 9t. And for z, same thing again. Z is equal to 2 plus 1t, or t in this case. Okay? So there we're already in our parametric form. And finally, the last form we want to work with is our symmetric form. I don't really spell this right. Symmetric, I think that's right. Our symmetric form. And in symmetric form, it's easiest to go from parametric. There's a lot of words going on in there. The blue will be best. We want to set this equal, our parametric forms. We want to set each of them equal to the value of t. Okay? So normally they write it as, I think it is, actually I'm going to go up to make sure I get the right parent form of it. X minus x naught over a. Okay. So x minus x naught over a is equal to y minus y naught over b, which is equal to z minus z naught over c. A quick way to do this is to take each of our parametric forms and set it equal to t. So, in our first one, we would bring x plus 3 divided by -9 would give us a t value. So that would be our first form. Okay. In our second one, we would get y plus 5 divided by -9 is equal to t. That would be our second form. And finally, I should have done that in blue. Our last one would be z minus 2 is equal to t. That would be our third form. So to write that all together, we have x minus 3 divided by -9 is equal to, I'm just going to scroll up to see it. Oh, sorry, plus 3. Y plus 5 divided by -9, which is equal to z minus 2. And all of this is equal to our parameter t. So if we ever wanted to find what the parameter was from 3 coordinates, we can just plug those 3 coordinates directly into here, and we would know what parameter would give us those coordinates along the line. Okay. Again, we can use all 3 of these to verify if points are on a line or not.